Yeah,
Okay.
go.
Hi, Professor. So we built the entire data path by starting with the ALU unit separately, and then we went on to build the data path including the memory, register file, and register fetch. So the beginning part is us building the ALU, and we have our own ALU operation, ALU control format for which we'll be designing a compiler for this on top of RISC-V object code. So for now, we have decided the following format for all the instructions which we require. I think we have included almost all the instructions which is needed, and we might update this table based on the requirements in future. So as of now, this is our design of the table, and we built an ALU unit accordingly. And this is our basic simulation of basic functionality, which we were able to run. And on top of this, Bia will be explaining the data path, and then followed by Manoj, uh, who will explain the simulation of the data path involving the memory unit and the register file separately. Bia, I'll hand over the screen sharing to you.
Oh, I thought that Minaj is gonna use
Yeah, yeah,
this.
yeah, I am. Yeah, go.
So there's three memory components of this project. There is a register file, an instruction memory, and a data memory. The instruction memory and the data memory were instructed to be implemented using the IP core components. So I'll focus on talking about the register file, which we were asked to build on our own. So as you can see, for the register file, we have a decoder that's trying to decode the incoming address into an enable signal, which connects to the four 64-bit DFFs that we have. Each should contain some kind of data in it that we can have access to. So decoder would translate that into an enable signal to enable one of these default flops. And in the end, they are all connected to a mux. The upper mux is for data out A, and the one below is the one for B. And according to the select signal that's connected to the mux, we would be able to choose which data from which of the 64-bit DFF that we want to output, and that would be register file. All of these components, 64 DFF, mux, and decoder, are actually written in Verilog. They're not the default symbols included in the Xilinx library. And if you want to check, you can see that in the reg.b file. They're all implemented as separate modules. And now, Manoj, can you take over and
So this is the final data path that we arrived at. So the data path was designed modularly as explained in the report. The stage one of the data path has a program counter that has a 8-bit adder. We use an 8-bit adder because our instruction memory is 32-bit by 512. So 512 would translate to an address of 8 bits. So initially these data instruction memory and the data memory were preloaded using a COE file. As you can see, first, as per our simulation model, we are saying that the first location is an OOP, and in the second location, actually the instruction set we use here is from RISC-V architecture. So from the document that RISC-V has provided. So here is my first load word instruction that would be loading with the data from data memory's address 0 to my register 2, and the next instruction is a load word instruction that would be again loading a memory from data memory's address 0, but this time into register 3. And then we are waiting for a couple of no ops, and then what we are doing is we are writing a particular data into the data memory's register 4. And just to make sure that our data is written to data memory, we are waiting for a couple of cycles, and then we are reading again from the same memory and writing it into a different register. After that, our stage 2 consists of a reg file that bio has created and explained, and then it also contains an instruction decoder which just generates our write mem enable and write reg enable signals based on the opcode of the input instruction. And later we have this pipeline registers that just take in the data and then take out the data. And here you can see the data memory which was a 64-bit 256 locations deep, and final register. And as you can see, from the final register, the write address and write data are coming. So this write back stage is for our load word location. So these were simulated, and as you can see in the simulation, here is our first instruction. So the entire design is a clear. So initially when clear goes to 0, our program counter resets to 0, and after when it goes back to 0, it starts counting and then executing a program. So in the simulation, when our clear is high, our program counter goes to 0, and as soon as it is gone, so for the first clock cycle, it's the first no op instruction, and then this is the instruction where we say that we want to load the data from data memory's address 0 into our register 2. As we can see, after 5 clock cycles in the register 2, the data of 4 is being present. The data memory was loaded with the data 4 in address 0 just to make sure that we don't get any garbage values. And then again we are asking to load the data from data memory's address 0 into register 3, and you can see that happening here after 5 clock cycles. And then we are trying to write some data into data registers address 4, and you can see that our data and the address are going in. And again we are just trying to read those and then bringing the same thing back into our register. And so here you can see in register 0 that we are bringing the register 4. So this simulation illustrates that our data path is working. We aim to deploy this on NetFPGA and make sure that it's running in our future labs.